All right. Let's get started. So now we're gonna be talking about well, the first page is a little bit different from the next. There's not 2 pages. Yeah. Okay, yeah, the first page is easy, so let's just go through that and then I'll explain something about like the precise definition of the limit definition of integration. But so for the number 7, well, the idea is we should try to draw these two functions, draw these two like integrals, and then from there, hopefully we can map it onto some geometric problem about calculating area. If we draw this A really carefully, trying to do that now. Well, we start off at 2 minus x. So we start off at 2, and then we want to extend this over by -3, which is going to bring this up to 5 here. So 5 and -3. And then we're going to extend this to the right by 5. Doing that's going to bring it down by 1, 2. So it's going to pass there, and then it's going to go down by 3. And so at 5, you go down to 3. And so that's what the function is going to look like. And then you can see that there's 2 triangles that we have to calculate the area for. So we have this triangle and this triangle. We're going to subtract one from the other. And it happens that this has a height and base of 5, whereas the other one has, charge this. The other one has a height and base of 3. So the way you can write this down is this is 1/2 times 5 times 5, so 1/2 times 25. Well, maybe I just write it as 25 over 2, just to save space. 25 over 2. Then the other one is going to be 1/2 times 9, but with a negative, so 9 over 2. And then when you subtract these two things, you'll get 16 over 2, which is equal to 8. For B, well, in the past I had to explain that this is actually a circle. So the trick of seeing that this square root represents a circle is suppose that we define this to be equal to y, and then look at like what happens when we square both sides. When we square both sides, we get y squared is equal to 1 minus x squared. And then when we move things over, we end up with x squared plus y squared is equal to 1. So this measure, from this point, it should definitely look like a circle to you. And just to get used to the fact that this square root representation is also the same thing. So this is a circle with radius 1. Really just a half circle because the square root only gives us the positive portion. And yeah, we're trying, this integral is saying find the area of half of the circle. So it's just 1/2 base times, or 1/2 pi r squared, pi times 1 squared. So it's just pi over 2. Okay, so that's number 7. Right, so number 8. Well, so hopefully you have looked at these problems. To read this right now is a little, it takes a minute to understand what this is actually saying. But the important parts are that we we want to think of our function as being a function that's always increasing. So we could, for example, draw something like this. This would be an example function that's always increasing from 0 to 10. And we want to compare the this integral with the approximation if you were to divide it into 5 pieces, left endpoint approximation, and the right endpoint approximation. So we want to compare like those two estimates against what the actual area would calculate. And the idea is to just take a portion of this graph. It all boils down to thinking about what it means for this function to always be increasing. So like take this section of this area. Okay, the integral is going to calculate this area exactly, right? The left endpoint approximation is going to approximate this area with a rectangle of the height in blue, well, green, sorry. And the right endpoint approximation, maybe I'll use a different color. It'll approximate with the height in red. And you can see that the green is an underestimate and the red is an overestimate. And that's all you need to know to do this. So that tells you the L5 approximation is actually going to give you, technically, it can match, depending. That's just a technicality. You could also not include those, the equal part. So yeah, the L5 approximation is going to be less than the integral, and the integral is going to be less than the R5 approximation. And this is all because the function is increasing, right? And you can think like, what would happen if the function is decreasing? You'll see that the integrals are going to, or the inequalities are going to swap. Okay. Any questions on this? No, thumbs up. Okay. All right. Yeah. So now we've got this left endpoint approximation, but this time we have a table. Right, so this first row represents like the x values, the values on the x-axis, and the second one represents the heights, so the actual function. And I guess the only important part is really the fact that we're using the left endpoint approximation and we have this set of values. So like, so say that we were to think about this visually. So we're going from 0 to 10, and we'll pretty much will be using the way that it gets chopped up here. So 2, 4, 6, 8, 10. The left endpoint approximation, you have to remember which x values it actually uses, because it doesn't use all of them. It turns out that the left endpoint approximation uses these values. It uses everything except for the 10. And just for comparison, the right endpoint approximation uses everything except for the 0. Okay. And so we can just set up we then think about this as just like summing up the rectangles. So each rectangle is going to have a base of 2. That's because the separation of the t's are 2. And then we just add together the heights. And so this is going to calculate the left endpoint approximation of the total distance. And if you just calculate this, you'll get 2 times 58, which is going to be 116 feet. Okay. So now 10 and 11, 10 and 11 are testing you on this sigma notation, which is most likely something you haven't seen before, but we start to show it to you here in Calc 1, and then you're going to get more hands-on with it with Calc 2. If you take Calc 2, where you start dealing with things like series and all of that. Okay. So 10 is actually pretty straightforward. So it's a sum of the integers, all the numbers, from 5 to 1,003. The easiest way you can do that is, say, we're going to sum the integers I, where I starts at 5 and goes to 1,003. So that's it. That's all you need to do. And it doesn't have to calculate the sum. If it did, that would be a bit more interesting. Yeah. But yeah, so we just need to write that. For 11, so now this is saying sum. So I takes for the values from 1 to 5 and then just sum up these all of these terms from this expression. So it's actually asking to sum 5 different things. One thing we can do, what in part of calculating this too actually can be pulled out of the sum. And that should kind of be clear because every single term, like as I goes from 1 to 5, that too stays constant. So you can kind of pull that out because it's just being multiplied against the I. The I is the thing you need to keep in there because it varies. And then, well, I guess what you would do is you would write this out in full because it's only 5 terms. If it was 100 terms, then you have to use a property about sums of integers from 1 to n. There is there's a closed formula for that, but most likely you haven't seen that yet. This is, I think, 15. Yeah, 15. And so you get 30, number 11. Simple calculation. Okay, does sigma notation make sense to you guys? Any questions on it? Thumbs up. Okay. No questions. All right. Good. Great. Okay. Now these last two are where I have to probably explain quite a bit. So okay, I should have checked this, but let me check it now. Whether the slides actually explain this well or not. What is this? Yeah, so give me a second to find this slide. If I can just copy something, that'd be great. Otherwise, okay. Where are we now? Oh, wait. His slides don't do that. It's weird. I'm missing something. No. How is that even possible? He didn't even explain it in the slide. The limit definition of number. Weird. Oh no, he does. But he just writes it all out. All right. Okay. So let's go through this construction by hand, I guess. So 12 is asking us to write basically, there's a definition for the integral in terms of limits. This is how you would define the limit. And we sort of are hinted at this idea somewhere in the previous homework, I thought. I'm not seeing it. Anyway, yeah, so what's the idea here? We have, say we're integrating from A to B. And we're subdividing it into n even parts. Okay, so the idea is that this integral a to b of f of x dx is a limit as the number of subdivisions, which I'm going to denote by capital N, as the number of subdivisions approaches infinity. And then you kind of then just have to think about how do you represent summing up all of the rectangles. Let's just make a representative rectangle here. Okay. So, well, n is going to go to infinity. You're going to need to sum up the rectangles, and then the summation, well, kind of, it depends how you want to index this. I would say probably you want to go from 1 to n, because there's going to be n different rectangles. And then we just need to think, how do you denote the height of the rectangle, and how do you denote the width of the rectangle? So, well, b minus a is going to be the overall length. And then if you divide this by capital N, this gives you something that typically you'll see it denoted by delta x. I'm using the capital delta, which is a triangle looking thing. So yeah, so this is the width of the rectangle. And now for the height of the rectangle, it's also a little, you have to think about it a little bit. So I'm going to make a coarser version of this so we can actually see the x values. So now that we know how wide each thing is, we can see that this tick mark is going to be a plus delta x. Okay, maybe I'll make it even further separated. So this tick mark is a plus delta x. This is a plus 2 delta x, and so on until you end up reaching b. So a plus 3 delta x, and so on. Okay, so and the way that choosing the height of the rectangle, the way that that works is, as long as you pick some value, any value inside of your subinterval, you then plug that into your function. That is going to be just an arbitrary choice of the height. And so, and one thing that you'll see that maybe the textbook show is you'd call this choice AI. Sometimes they use a star. I could just probably use an AI. It's just a choice of a point inside the subinterval. So for our purposes, we'll probably just use one of the endpoints. So what this means then is we end up having a formula for a plus I delta x for the value that you plug into the f of x. And so in abstract, this is going to be written like this. This is representing the height times and then the width. So you have this whole thing. This is the definition, the limit definition for an integral, which you can, yeah, exactly. So yeah, Craig's slides has it written in exactly the same way. Yeah, the only thing is, like, usually you want to compactify the notation used. So instead of writing a plus I delta x, you would just call this xi, where xi is as defined. Okay, so now let's take this definition and use it for these two problems. So you want to write down a limit that is equal to this. So we want to take a limit as the number of pieces, the number of subdivisions, goes to infinity, of a summation. I goes from 1 to n. And now the length of the interval we're integrating is going from 0 to 5, which tells us that the delta x is going to be 5 over n, and the xi is going to be, so notice that like it would be 0 plus, right? It will be 0 plus I delta x, but then we can just simplify what that actually is. So it's going to be 5I over n. And then we end up just plugging those things into our expression. Oh, f is given to us as well. That's just sine of x squared. So this xi is going to be what we plug in for x inside of the integral. So we end up with 5I over n, which then ends up being squared, times the delta x, which is 5 over n. And you can check that this really does match up with the limit definition that I've written off to the side. So you have the function, you're plugging in the xi, which is this 5I over n, and then you've got the delta x. Okay, so that's number 12. And now 13 is asking us to go in reverse. So there are a couple of differences though. The biggest difference here is it actually tells us I starts at 0 and goes to n minus 1. That's maybe seems a little bit strange to you, but in fact, the way you think about this is you can compare this summation against this summation. Going from 0 to n minus 1 versus going from 1 to n, you'll note that you still have n different terms. So really the way to think about this is a shift of this summation. It's the term is re-indexing. So you could re-index the sum so that it starts at 0. But I think it's more natural to think about it in terms of I starting at 1. Okay. And maybe we'll label certain things. So we would expect this to be the delta x, and we would expect this to somehow be the, so this here I have to be a little bit careful because there's actually two different ways we can interpret this, and they'll give us two different limits. I'm gonna interpret just this portion, and maybe I'll compare against the other one. But if I just can treat this I over n as being dxi, then notice in this case, the function would then be f of x is equal to 2 plus x quantity squared. And the going 1 over n. This 1 on top tells me that the integral is going over a length of 1. And this xi is telling me it starts at 0. So it starts at 0 and goes up to 1. And this is where that 2 plus thing kind of makes a difference. If you include the 2 plus, the xi ends up, or if xi includes the 2, then the way you would interpret this is that this interval would be from 2 to 3. And the f of x would just be x squared. But then everything else works out fine. So let's just form this into an integral now. So this is saying 2 plus x quantity squared dx. So that's what all of this information says. And just for comparison, I'm going to use a different color. Suppose that we had xi be equal to the whole thing. I just find this a little bit curious that it works out this way. This is kind of almost U substitution. You already know what that is. So if we were to take xi to be the whole thing, then the function would just be squaring. And this 2 plus, this 2 would actually be the a in the formula, a plus I delta x. Delta x is still 1 over n, but this time this 2 is saying we start at 2 and then we go for a length of 1, which gives 3. And the integral that you would form in that case would be integral from 2 to 3 of x squared dx. And it is like these two integrals are actually equivalent to one another. They only differ by a shift, which you can actually do by actually performing a U substitution once you learn what that is. Or you could just check this now by actually taking an integral and seeing that the two integrals actually give you the same value. It's curious that that works. Okay, so that's all the homework for today. Are there any questions? No, no questions? Okay, then yeah, we'll